The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So let's get started. This is my last lecture of the class, and I want to thank you guys. This has been a really good class. I really enjoyed the good questions on the forum, especially. I don't know if you guys enjoyed it, but I liked it anyway. So I'm going to give it. My lecture here is going to be a wrap up on the stochastic methods, and then Professor Swan's going to give a review on Wednesday. It'll be the last lecture of this class. And then the final is a week from today, I think. That's right. Morning? Yeah, morning. All right. All right. So as you did in the homework, and we talked about, there's a lot of multidimensional integrals we'd like to be able to evaluate. And a lot of them have this form that is a probability density times some f that we're trying to evaluate. That's the integrand. And then I didn't draw in the millions of integral symbols around it. But usually x is a very high dimensional thing. So you have to integrate a lot of things. And often, we actually don't really know p. We know a weighting factor, w. So I just drew 3 of the integrals there, but there might be 10 to the 23rd integrals there. So w is a lot easier for us to deal with than anything with all those integral signs. So for example, the Poisson distribution is one of these things. And also, just recall back earlier, we were talking about models versus data. The Bayesian analysis of experiments says that you take your likelihood function, the likelihood that you would have observed the data you did if the parameters were true for certain values of theta, and then you multiply that times the prior knowledge of the parameter values, and that gives you the weighting factor really for any integrals involving parameters, because it's really giving you the w of theta, given everything you know. You know prior information, and you also know the new data that you measured. And put them all together, you get the weighting factor for the parameters. And so you can evaluate all kinds of multidimensional integrals over all the parameters in the problem. So very often you might do experiments where you maybe have 4 or 5 or 6 adjustable parameters, theta, some of which you know something about ahead of time. And you want to put them together this way, and this would be a summary of everything you know. But it's sort of a goofball summary because it's a function. It's a multidimensional function, right? A function of a lot of variables. But now you know how to do integrals of functions of lots of variables, so you can compute things like some linear combination of what's the expectation value of some function of those parameters. So if f here was a function of theta. Why is it bouncing? Okay. I was wondering why you guys are always looking like this. All right, so f of theta, you can have any function you want, you can evaluate. It's a function of the parameters, like prediction of what will happen in some new experiment that depends on the parameters. You'd have it as f of theta, and then you could integrate it over w of theta to get the expected value of the result of the new experiment, and also actually the distribution you have to get that way. Does this make any sense? I see one person thinks it makes sense. Okay. So just because we did Monte Carlo using Boltzmann, which is a common one to use, there's other weighting factors. I guess that's my comment. And anytime you end up something that has some integrals with weighting factors, then you should think, oh, I can use Metropolis Monte Carlo. And also, anytime you have experiments, a lot of times you think of the, okay, I want to get the best fit least squares approach, which is what you already knew before I taught you anything. But it's very important to remember that you can also write the actual probability density, the shape of the probability density of the parameters. And that way you can get all the correlations between the parameters and include all the previous knowledge of the parameters and stuff like that. So that's a very important thing to remember from this course, is this Bayesian formula. All right? But Metropolis Monte Carlo, as you saw in the homework, is not always that easy. So you need to choose the step length in every dimension. It's sort of the factor you're going to multiply times the random numbers to figure out how far to step from one state to the next. And it's not so obvious how to choose that before you start, because you may not know that much about the shape of the integrand, right? Actually, even of the shape of the P, the probability distribution, you might not be that sure about it. And so if you accidentally choose it too large, what will happen is it tries to take big steps away from a probable state and ends up at really improbable states, and then most of the times it won't accept that transition, right? Metropolis Monte Carlo will just repeat the same state over and over again. So if you see that you just keep sitting there getting the same value over and over and over again, then that's warning you that you must have chose your step size too large. Alternatively, if you choose it too small, all your steps will be accepted because you're not moving anywhere. So you're basically staying at the same point over and over again, except it's slightly different because you took a little tiny step. But that way you won't necessarily sample the whole range. And you can see that by plotting, say, the distance from the initial state position. So you have you initiated the Monte Carlo Markov chain at some state, and if you plot probability distribution of density, the distance of all the new states to the original state, and if that number is super teeny tiny, then you might be a little bit concerned that you really didn't cover the whole space. But again, you have to know what's super teeny tiny, so you have to have a range in mind. Yeah?
Can you do this adaptively?
Yeah. So good algorithms for this try to pick it up, that there's a problem. Like if it keeps on either not accepting any states, it would try to shrink the step, the delta, or if it's always accepting the states, then it might try to increase it. And you want to have the delta, you want to accept actually most of the transitions because it makes it more efficient, but you don't accept them all. So you want to, there's some, I don't know, keep it to 0.9 probability or something like that, 0.8. And there's probably a whole journal paper about what's the optimal way to do the adaptive step sizing to get this to converge the rest. Yeah?
How would you prevent your initial guess from biasing your overall integral? How many steps should you throw out?
Well, to me, I don't think that throwing them out is a good idea. I don't know. People do it. I think it's that you really just make enough steps that you are sampling everywhere, and then it shouldn't matter. And a good thing to do is actually start from some completely different initial state and make sure you get the same value of the integral. And that'll give you a lot more confidence that you're not sensitive to it. If you're sensitive to it, you're in trouble because you won't know how many to throw away, and you don't know if you actually even achieved the real integral. Like you can, I think in the hydrogen peroxide example, actually it was symmetrical, so it was a little bit, didn't matter too much. But if I had given you an asymmetrical one, there's like, here's like the dihedral angle. It has to do with the orientation of the H, like sort of out of the plane. And it should be symmetrical, that you can kind of sort of have plus and minus, and there's like a high probability region over here and a high probability region over here. And you start in one of them, say over here, and you just sample all around here. You get a lot of points, all have basically the same value dihedral angle. And you never see any of these, then it's no good, right? Now, in this particular case, you might still get the right answer by luck because they're exactly symmetrical. If this one was a little bit asymmetrical, then you get the wrong answer. Does that make sense? So you really want to make sure you're really sampling over all the physically accessible region. So, but again, this is a common problem for us all the time, is that when you're doing a calculation, you want to know what the answer is before you start. This is an absolutely critical thing. Because how the heck are you going to know if you have a bug? Right? The computer's going to give you some number at the end. You have to know what the number, actually what the answer is before you start. I know this seems weird, right? But anyway, it's the truth. If you're going to calculate anything, you really want to know what the answer is roughly. You know, what the units are, what the order of magnitude is, some things about it. And ideally, you should try to think of some simple test you can do to try to check whether your code's right, whether things reasonable. You know, the reasonableness test is it reasonable that was what you get. So this is the same kind of thing. Like you draw the H2O2 and say, oh, I think the dipole moment should be about such and such because I know the charges, typical charges are an H atom and O atom. And if you get some number that's way off from that, then obviously you made a mistake somewhere, right? It could be a mistake in your code, or it could just be you just didn't sample correctly because your delta was wrong, for example. All right. Now, I know I've told this to students every time, and every time I tell it to students, they look like you totally reject this idea that you should know the answer before you start. But it's absolutely critical. I mean, it's my whole job as a professor is I tell my students, please calculate this. But before I tell them that, I know what the answer is, right, roughly. And so that way when they come back and show it to me, I can say, oh, it's reasonable. Okay, I believe them, you know. So I think the number should be 20, and they come back, it's 14.3. I say, 20, 14.3, they're pretty close. Okay, so I believe them. If I think it's 20, they come back as 10 to the minus 6, then I'm pretty confident. I tell them, I think you must have made a mistake. And they're like, no, I did a great job. I'm sure my calculation is perfect. And then I'm like, you know, I'm really probing. And they think I'm like, I don't know, I have it in for them. But no, actually I knew the answer, what the answer is, so obviously it can't be right. So they must have made a mistake. Anyway, you should be like too. You want to be able to be self-critical about what do you expect your answers to be before you do them. All right. What else is problematic with Monte Carlo? This is very problematic. If you want to achieve high accuracy, you need a really large number of states. And it's funny, it's like you can get a pretty good accuracy with not very many samples because of the behavior of 1 over square root of n. So it's like it has very big changes at small values of n. And just a relatively small number of samples, you get something that's halfway reasonable. But then if you want to get, if you have 3 significant figures and want to get the 4th one, it's a killer because you have to do 100 times more effort, 100 times more samples to get one more significant figure. And so you've already done 100,000, and now all of a sudden you have to do 10 million samples, and then you want to get one more significant figure after that. Now you need to do 1 billion samples, and it's like this gets really out of hand. So that's a really unfortunate thing about it. But the nice behavior at the beginning is you get roughly, if you only want a few significant figures, you can get them pretty darn fast with Monte Carlo. It's certainly a lot better than trying to do the trapezoid rule in multi-dimensions or something like that. All right. So you guys just did Monte Carlo. Are there things I should tell you about or we should talk about or problems you run into? Now, you see, when I set that homework problem up for you, I helped you out a lot. I don't know if you noticed that. So the original problem had, it's 4 atoms. They each have 3 x, y, z positions. So there's 12 coordinates. And then I did clever tricks to get it down to, I think, 6, maybe? OK. So going from 6 dimensions to 12 dimensions, that's actually a pretty big deal. And so if I've been giving you the original 12-dimensional problem, you can still compute it and actually use the same kind of code as you wrote. But the number of samples you need to get a good number gets really wildly different, right? And so, again, this has to do with knowing the answer ahead of time. I knew, okay, that the magnitude of the dipole moment doesn't depend on the orientation of the molecule, so therefore I'm going to get rid of all the rotational degrees of freedom. I know it doesn't depend on the translational position of the molecule, so therefore I get rid of all those. And so, before I even did any calculation, I can tell you, I can get rid of 6 degrees of freedom, so that'll help you a lot. But it's a similar kind of thing. You want to do that all the time yourself, is try to think, what can I do that's easier than just doing the brute force problem? Yeah?
So on that problem, changing the max step size, you could change the percentage of steps that are accepted.
Yeah.
And I think the mean stayed roughly around the same, but the shape of the distribution actually changed a little bit.
Okay.
So
yep. So I think it might be this kind of thing is one part of it. It's like if you only integrate, say, one lobe of the dihedral, you actually get a dipole moment value that's pretty reasonable, even if you totally miss this other lobe. But if you did a different step size, you might start getting some samples over here too. And so the distribution would look a lot different, but you still end up getting the roughly the mean. But also, it's partly that the good thing about the Monte Carlo method is that the first few samples, no matter what they are, give you something that's on the order of magnitude of what the value of the thing is. So even a really lousy sampling at the beginning still gives you something that's halfway reasonable for the average.
So if you're trying to recreate the overall distribution of the histogram,
yeah.
Then how do you know which max step size to choose? Because that changes the shape of the distribution.
Yeah, so the rule of thumb I've heard is that people try to get an acceptance ratio between 0.2 and 0.8. So it means, you want, yeah. But I really don't know. I'm not an expert in this field, but I'm sure you can read papers and people have big discussions about what the acceptance ratio should be in order to taking big enough steps that you have a chance to get the weird stuff. In this kind of one, it might be kind of a problem. If you're doing steps, say, in the dihedral, you might have to step quite a long distance to find the other lobe. So sometimes having some pre-knowledge about what you think the shape of the things are is a big help. Yeah? No? Sorry, maybe I didn't answer your question. Is that?
Yeah.
That's good. Yeah. All right. All All right, so that's Monte Carlo. Then we talked about the more difficult problem of where the probability distribution is not stationary. And in fact, we don't even have the W written out. All we have is a differential equation that divides the probability distribution. And we did it here for the case of discrete states. And that's the right one to use, for example, for the kinetics equations, if you want to get them exactly right. Now that differential equation looks really easy, right? It's just a matrix times P. It's a linear differential equation system. You knew how to do that one probably in your second semester of undergraduate, taking differential equations class, right? They did diagonalize the matrix. Yeah? Remember this? So that looks really simple. But the problem is that the number of states is so big. So have any of you tried problem 2 on the optional homework? Anybody try? Has anyone even looked at it? I know somebody looked at it because I got some question about it. All right. At least one person looked at it. Let me tell you guys briefly what this problem is. It's a really relevant problem. If you go work for Professor Jensen, Professor Bratz, maybe Professor Roman, you might end up doing this calculation. So this is not a crazy calculation. It's very simple. All we have is like a chessboard of sites on a catalytic surface. And they had some number of sites. And this is what, if you take a crystalline catalyst and cleave it, you'll have a whole repetitive pattern on the surface. And somewhere along there is some active site that does something. You can tell that experimentally because you stick that catalyst in the presence of some gases, you make products that you didn't make when it wasn't there. So it did something. So the way people model this is to say, okay, there's some active sites on here, and there's probably one of them per unit cell, maybe. And the site can either be empty, like if I have ultra high vacuum, I pump on it and heat it, should be nothing there. And then if I expose it to a little bit of some gas A, some of the sites might have A molecules sticking on them now. And I also expose it to some sites, gas B, maybe one of these sites might have a B molecule in it too. And if A and B can react and make my product C, then maybe if they're sitting next to each other, they might react with each other. Okay, so this is the whole way you look at this problem. And so all I want to know is, if I have some A's and B's sitting on the surface, sort of, how often they're going to react. And the problem is a little bit more complicated. It says, well, suppose I also know if I put a whole lot of B on the surface, what I end up seeing is coke. My whole surface gets totally coked up. So let's model that by saying, well, suppose two B's are next to each other. They have some probability of reacting to turn into some coke product that sticks there permanently and just poisons the catalyst. Okay? And this is real life too, right? So if you're trying to run a catalytic process, a lot of times you have to run with one reagent in great excess to keep the surface kind of clean, keep it covered by the unharmful reactant, and then you let little bits of the other reactant come down and react with the A really quickly. But you don't let too much of the second reactant come down because it might cause a problem like dimerize or coke or something. Okay, so that's the model. So I have, some of these guys have A's, some of them have B's. And if, in the unlikely case that two of these guys react, they both turn around and then turn them into S's. Coke, soot. And then that part's dead forever after that. Okay, so that's the model. So in the case that they had 100 sites. I think it was 10 by 10, if I remember correctly. So it's 100 sites, and each site can either be empty, or have an A molecule, or have a B molecule, or have a coke molecule S. So there's 4 different states on each of 100 different sites. So how many states are there all together? It's 4 to the what? 100. Okay, so that's a pretty big number. So that's how many states? It's about 10 to the 60th, I think. All right, so this is a very large number. This is bigger than Avogadro's number. This is really a lot of states. You wouldn't have thought that just a stupid little problem with just a 10 by 10 piece of catalyst and, and 3 different things that can stick there would give you so many numbers, but it does. So now I have a problem that if I have, if my P vector is now a probability that has a number for each of the 10 to the 60th possible states. And then the matrix M is that number squared, right, dimension. So it's 10 to the 120th power elements inside the matrix M. So even though the matrix M is very sparse, this might still be a problem because 10 to the 120th is really big. Okay, and your computer can only hold 10 to the 9th or 10 to the 10th numbers in it. So this is going to be a problem. And also, that's not just what p is. That's what p is at this instant, say 1 millisecond after t naught. And then if I wait to 1.1 milliseconds after t naught, p will be different. So I have 10 to the 60th numbers that change with time in some way that I don't know. Okay? So this is actually a really hard problem to solve it. And so everybody uses kinetic Monte Carlo to do it, because there's no way I can possibly even list all the elements of p. And in fact, if I sample, if there's 10 to the 60th states, no matter how good my sampling algorithm is, I'm never going to sample 10 to the 60th states. So there's a lot of states I'm never going to get, not even get one sample of. I'm just never going to encounter them at all because there's just too many states. But anyway, people do it anyway. So we go ahead and we'll do the Gillespie algorithm, which you guys, we talked about in class. Now, to compute a Gillespie trajectory, we have to compute two random numbers, right? We compute one random number that tells us how long we wait until the next thing happens. And then we compute a second random number that tells us which of the many possible things that happened actually happened. And so if I have a case like this where I had the original case, you know what can happen? The A could react with the B could react with the A could come back off, the A can move to the next adjacent site, the B can move to the next adjacent site. A lot of things can happen, right? So there's quite a variety of things can happen from this initial state. And so you have to, if you're solving this problem, you have to write that down. Yeah, jump up.
So the exponential waiting times are so where really completely dependent on the process, like where we have it, you know, we decide there's going to be an arrival, and then we just allocate some arrival time by that exponential random variable.
Yeah.
And then we make something happen. But I mean, I feel like you could run the exact same simulation without counting the times, get the same answer, and then after the fact come and strap some times between events into the system. Like, it doesn't seem to be coupled, that the time into the...
Yes, that's right. Yeah, that's true. So it's you only do the time calculation because you care about the time. If you don't care about the time, you only care about like the steady state solution, then you can probably do it some other way.
I mean, you don't need to calculate the times inside that loop. Like, you can calculate the entire like state space trajectory without any reference to time.
Yes. Yeah, so you could get the sequence of all the things that happen without, if you didn't compute the time, because it doesn't matter, right, for the time. It just means the sequence of what happened.
Yeah.
The sequence of states is all that matters. But if you want the kinetic information, then you also want the time, because it might be it's sat in one state for a million years, and the other state.
You can generate that off.
Yeah, yeah, that's right. Let's go ahead. Okay, so make this cheaper. Make it one random number per check. Yeah. Okay. All right. So. Things just keep in mind about this. So it's the cost here is computing random numbers. We have to compute at least, well, some number of random numbers. I don't know how many. And that number depends on the length of time I want to simulate and what my delta t is, where the delta t is sort of like the average time between events happening. It's like 1 over a in the Joe Scott's notes. And so if that delta t is very small and my time I want to simulate is very large, that means that each trajectory is going to have a lot of events. And that means that we have to generate a lot of random numbers. And so generating one trajectory is going to be really expensive. On the other hand, if the delta t were about the same size as the total time I'm simulating, then I might only get 1 or 2 events. And so I only have to generate 4 random numbers for each sample. All right? And I just have to keep in mind that I'm going to have a lot of low probability states that I'm not going to sample at all. I might even have some high probability states I don't sample because I just can't do enough samples. And I have the same exact problem I have with the Metropolis Monte Carlo and with all these stochastic methods, that the scaling is 1 over square root of n. So I can get a rough idea pretty easily, but if I want to get a really precise number of anything, then I'm going to have a problem because I'm going to have trouble to do enough samples to really refine the number. A key thing in this is that with anything like this, where I'm going to have so many states, I'm going to have to run a lot of trajectories to all sample all the things that can happen. And so I'm probably not going to be able to store all the trajectories I ran on my computer because I'm going to run so many. And so I really want to compute things on the fly, which means I should decide ahead of time all the averages, all the Fs I'm trying to compute, So I might want to compute f and f squared and I don't know, whatever else I want to compute. The average value of the number of A's on the surface. I mean, there might be a lot of diagnostics I can compute to just check everything's okay. Think of that beforehand, code it to compute them as it runs, and that way I only have to store the running averages of all those quantities, and I don't have to store anything about exactly which state sequence I hit. Is that okay? All right. Now, if you remember, in this equation, there was an initial condition on the right-hand side, which we totally ignored so far. But that's actually pretty important. And in a lot of real cases, from your macroscopic continuum view of things, you have an idea of the average value of n's. And what you don't know is about the discreteness, and you don't know about the correlations. All you know is sort of an average. I expect to have, 2 A's and 3 B's on the surface or something from the partial pressure of A and B and the binding constants of A and B. So I have some idea. So I think I know these averages. And so what people usually do is they use a Poisson distribution for the probability of the exact number of A's. So suppose I think on average I'll have 2 A's. Well, I might have 1 A, I might have 3 A's on the surface. And so I'll just use the Poisson distribution of n to get an estimate of sort of the expected width of the distributions. And so that's the formula for the Poisson distribution. You have to know the average values of NA, NB, and C. And then you can see that the n appears in the unaveraged n appears in the exponent and in the factorial. You see that? All right. And so really every time you start a new trajectory in kinetic Monte Carlo, what you should do is sample from the Poisson distribution to get a new initial condition as well. Okay. And that way you're sampling over both all the possible initial conditions and all the possible things that can happen to them to really get the real average of what you might want. All right. Now, we just realized how horrible this problem is because it has so many states. And so then we're going to have to think immediately, what can I do to make this faster and easier? And so here are some things people do. One thing is that people try to figure out what are the really fast processes, and do I care about them? And some of the fast processes you might say, well, like diffusion of A moving to here, and then it moves to here, and then it moves back to here, and then it moves back to here. That's like of no interest to me. I don't care where the A is bound on the surface. Right? The only way I care about it is whether the A reacts to the B when it's sitting next to it. In other respects, I really don't care about the diffusion. So having the time constant for the diffusion be the real time constant might not be that important. So then you can do different things. One thing is you can assume it's infinitely fast, and you sort of like say, well, every time I look at a site, I assume that this A has a 1/10th chance of being here, 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 all these different spots, just as if it's equilibrated around all the empty sites. That would be one possible way to do it. That's the infinitely fast diffusion idea. Another idea is to say, well, let's slow down diffusion to make it slower, just to help out our computation. So I say, well, on average, I might get one reaction a millisecond. In reality, the diffusion time is a nanosecond, but I don't care about all that nanosecond stuff. Let's pretend that it's a 1/10 of a millisecond. So it'll still be pretty much equilibrated on the time scale of the reactions, but that way I'll be able to accelerate my calculation by 7 orders of magnitude by going from a nanosecond time scale to a 1/10 of a millisecond time scale. So there's a lot of different tricks like that. And if you read a paper that does kinetic Monte Carlo, you got to read exactly what they did. But they usually do something like this because it's just totally out of hand if you try to model everything perfectly. You also, the low probability events, the really low probability events, you're never going to sample. So if I have some process that happens on my catalyst that takes 10 hours to happen, and my main reaction happens in a millisecond time scale, I'm never going to be able to run out to 10 hours. So I might as well just forget it. So if I know experimentally that the coking thing only happens on 10-hour time scale, I just take that out of there. And I don't have to clutter up my calculation with all these S's. I'm not going to form any of them in my time scale anyway. And so therefore I cut the number of states. Instead of being 4 to the 100th, now it's 3 to the 100th because I got rid of all the coke. And so now I've drastically reduced the size of my problem. Not often you can do a reduction like this. That's a pretty big reduction in the size of a problem. All right. And then you have to have an idea of what adequate sampling is. So you're going to see some lower probability processes compared to some higher probability ones. And you have to know when are these low ones so small that they're statistical noise. And this is the margin of error problem. Do you ever see polling, like in the political polls, they always say, you know, so and so many people believe in evolution, plus or minus something, right? Well, the way they get the plus or minus is from the square root of the number of samples with a positive result. So the margin of error on low probability things is much larger. So the number of people who believe that Professor Green is God is a very small number. So if you find somebody like that, you have to figure they're within the margin of error, right? Okay. So, but you know, the number of people who are going to attend 1034 this morning is, you know, a big enough number that the margin of error in that is, you know, maybe 2 or 3 people. It's not going to be 100 people. Does that make sense? All right. So the more likely the event is, the more likely you'll get a lot of samples of it. If you count the error as roughly the square root of the number of samples you got of that event, then the statistical error in your sample of the high probability events won't be that large, whereas for the low probability events it could be really gigantic. All right, so just for an example, in the main reaction A plus B is really fast because it's a good catalyst. So I'm going to get a lot of trajectories going to show that reaction. So that's good, and I should get good sample statistics. But the coking reaction is really slow. At least I hope it's slow. Otherwise, the catalyst is no good. And so it's really slow. I might not get very many of those guys. And so even if I left it in the calculation, I might not be able to reach any conclusion because I might only see one coking event out of all the 100,000 trajectories I run. And so then I won't know whether to say anything about that or not. And then if I let the diffusion in and it's too fast, then my delta T is going to be too large, which means that my CPU time to compute a single trajectory is going to be too large, which means that I won't be able to get good sampling because I won't be able to run very many trajectories. So I might want to do something to get rid of that. All right. Now there's another method that a lot of people use. I think actually Professor Swan uses this sometimes. Is that correct? Yes. So this is another method. And what it is you solve the equations of motion of the atoms or clumps of atoms, typically using Newton's equations of motion. And typically people use it using force fields that were fitted to some experimental data and maybe with some quantum chemistry data as well to get some idea of the forces between the atoms and the forces with which the molecules, when they bump into each other, how they interact. Typically it's done classically using Newton's equations of motion. But if you don't like that, you can put in the quantum mechanical effects in a couple of different ways. And my group's worked on one way called RPMD. And you can get pretty good agreement with the quantum chemical results by doing this fancier version of molecular dynamics. So there's some different equations you solve, but basically the same. And so you can do it. And there's a nice algorithm called the velocity Verlet algorithm that almost everybody uses in this field. And what's nice about that one is that it can do a lot of steps of moving the atoms around. And after you do 1,000,000 steps like that, you compute the energy by adding up all the potential energies and kinetic energies of all the atoms. And it'll still be about the same energy as you started from. Whereas a lot of methods, if you do the integral like that and you calculate the energy at the end, it won't be the same as the energy you calculated because the methods have little round-off errors and they kind of accumulate in a way that messes up the energy. And so this particular algorithm is a nice ODE solver method that is good has a property that is good for conserving the energy. And then a lot of people use a thermostat because they care about samples that are in contact with a thermal bath. So you're sampling a few molecules, maybe 100 molecules or 1,000 molecules, but not 10 to the 23rd molecules. So you have like your 100 molecules or your 1,000 molecules, and you pretend that they're in contact with some bath, and you're watching those 100 molecules wiggle around. And their energy is not exactly conserved because they're exchanging energy with the thermal bath. And so there's different things called thermostats, which are computer ways of sort of adjusting the velocities of the atoms periodically as if they got a kick from the thermal bath that makes them go up or down. And that's very important if you're trying to do, say, chemical kinetics, because the reactions are so slow that most of the time you watch the atoms wiggling around, nothing happens. You need the unusual case when you get a big kick somewhere that gives you enough energy that you can overcome a barrier to make a reaction happen. All right, so that's what molecular dynamics is. And numerous people in the world and in this department and on the campus do these kind of calculations. And there's kind of two ways that they're used. One way is used as an alternative to Metropolis Monte Carlo. So you're trying to compute basically multidimensional integrals, basically from statistical mechanics integrals, more or less. And instead of using Metropolis Monte Carlo, you decide to use molecular dynamics. This is a tricky choice between those two options. Nice thing about the molecular dynamics is I didn't have to choose any step size, basically, right? It's like the time scale is set by the real physical motions of the atoms. And if I don't want to think about it, I can just put in what's the real physical time scale of the vibration of some atoms. And I don't have to think about it at all, just run it. But something you should be a little bit thinking about is the molecular dynamics equations we're solving is really a time-accurate method. We're trying to we can actually get real time dependencies. We're using the real physical time, which turns out to be pretty darn fast. So molecular vibrations are time scales of like tens of femtoseconds. And so that's really fast. And so you have a really tiny delta t. But if you're trying to actually compute a steady state property, then maybe this isn't, it's not necessarily the best way to do it, okay? Because you're doing something where you're doing extra effort to sort of keep the time accuracy. It's sort of along the lines of John Paul's question. If you're doing kinetic Monte Carlo, if you didn't really care about the time, then you don't have to spend time computing the time, right? And it's the same thing here. Is if you don't really care about the time, then you might want to use the Metropolis Monte Carlo instead, because if time's not really in your problem, then you can kind of tailor it to take steps that don't really have to be physical or related to physical amounts of time, and you can still get the right integral. Whereas here, it's going to necessarily do things that are exactly the physical amount of time. And some processes in the real world are pretty darn slow, at least compared to 100 femtoseconds. So you might have a problem with trying to compute by a time-accurate method. Now, on the other hand, sometimes you want to compute time-dependent properties. And this is more or less an exact simulation of what the molecules really do on the time scale that you're simulating. So if that's what you care about, like what's happening on the time scale of like picoseconds, nanoseconds, this might be exactly right because you're actually simulating with a tool that's time accurate on the time scale of what you're really trying to measure. And so some chemical reactions, some kinds of energy transfer processes, like Professor Tisdale's group has exciton transfers that are happening on like picosecond time scales. It's like tailored to that kind of problem. Okay, but this is the limitation. So you have to use a very small delta t. Therefore, your total time is typically limited to nanoseconds as far as you can integrate, because you have to, if you just count how many time steps you'd need. And so if you're trying to determine some kind of static equilibrium property, you start from some initial gas at the positions of the atoms and the initial velocities. And then physically, it takes some time scale for that initial gas to sort of relax to the real equilibrium, because you don't know the real equilibrium situation of the system. And that time scale, if it's longer than nanoseconds, you're in trouble because it's not going to be done before you've done the calculation. And you never even achieve the equilibrium situation. Also, if you have a situation like that hydrogen peroxide case we talked about, suppose it takes a millisecond for the hydrogen peroxide to change conformation from the dihedral angle being one way and to be the other way. If I can only simulate for a nanosecond, then I'm never going to see that happen. So I'm never going to jump from the one conformer to the other. On the other hand, if I cared what happens inside the one conformer, everything inside there probably happens on nanosecond timescales. And so I'll get the really good sampling of what's happening inside the one conformer. And similarly for the dynamic processes, if you have a process that happens at sort of nanosecond timescale, this is really the ideal way to do it. If you have a process that's happening on millisecond or seconds or hours timescales, then this is not really the way to do it at all. And then there's an initial condition problem with this. It's kind of related to the kinetic Monte Carlo initial condition problem. So in the kinetic Monte Carlo, we had to sample over all the possible initial conditions. We did it with a Poisson distribution. There's a similar issue here, is how do I set up the initial conditions? Where do I arrange the atoms to be to start out? I really want to sample over all the different possible ways the molecules could be arranged. And particularly if I have say I have a protein, and the protein has some conformation it likes to sit in, and then it can unfold and go to some other conformation. Maybe there's 2 or 3 conformations like this. The timescales for those changes, again, might be milliseconds. I'm not going to be able to follow them with the molecular dynamics, so I need to have some sampling method to set me up in each of the different conformations that I want to sample. And then I can follow very accurately what would happen over a couple nanoseconds after it's in that conformation, but I'll hardly ever see it actually achieve the other conformation on the time scale. So I guess what I want to say to you guys is these are different tools for really different purposes. The Metropolis Monte Carlo, the Kinetic Monte Carlo, and the molecular dynamics, they're all good for some kinds of problems, but none of them is good for all problems. And I often get journal papers where somebody uses the wrong method for the wrong problem, and so I have to reject it. I've often had people come to want to do postdocs for me, and they talk about the thesis, and I see the poor kid, he spent 5 years of his life using the wrong tool for the problem he's doing. It's very sad. So don't that be you, okay? So don't just use a tool because you know it. Think, is this tool work for this problem? If not, I got to find a new tool. And just make sure you're using tools that match the problems you want, that you're trying to solve. I think that's all I got. So I have 10 more minutes left in class. Any questions you guys have? Yeah.
Just had one on the weighting functions for the Monte Carlo simulations. I'm still a little shaky on how you always determine those. It seems like it was kind of given to us on the problem we did on homework, and then in the exam in class, you just like set it to an even distribution or a uniform.
Yeah.
How do you choose what's best? How do you know what you're supposed to do?
Yeah. Well, yes. This is like, so you get some integral. It's integral of g of x something. Right? Where this is a lot. And then you have to figure out, what am I going to do so I can solve this thing? And the clever thing is to figure out, can I rewrite this as p of x times f of x? Because I know how to solve those kind. And actually, I don't even, and even if I don't know what p is really, maybe I can write it as w of x over some number of integrals here. That'll be my p of x. So it's most of these things you can do with uniform distributions if you want, but then your sampling can be extremely inefficient because you'll sample a lot of regions that have very low probability of being really there. So, but this is like a cleverness thing about, can I figure out what's the p times f that's equal to g that's going to work the best for me, and work the best. That's a good question. So one way of working the best is if f is most constant. Because if f is perfectly constant, then I get the right answer in the first sample. Okay? So that's one thing, is trying to figure out f to be really pretty constant. The second one is to try to figure out p that's like very sharply focused. So I don't need to sample a lot of x values to get it. Now these two are kind of at odds with each other, the sharp p and the flat f. So, there's probably whole people wrote their PhD thesis in applied mathematics about what's the optimal choice of p and f. A lot of times, I'm not that smart, so I just if I have a problem with StatMech, I'll always do a Boltzmann factor. It may not really be the best thing to do, but that's what I would do, right? And if I am doing a Bayesian problem, it's sort of like the W is given to you, right? Where is that? I know that's the formula I know, so I'm going to use that W. Maybe there's a more clever way to do it, but that's what I normally would do. Actually, one thing that I don't know if we ever talked about explicitly, but it's very important to know, is that this kind of formula, these formulas have, say, this W of theta. That's the joint probability that theta 1 is something, and theta 2 is something, and theta 3 is something, and theta 4 is something. It's that probability density. But a lot of times you don't care about that level of detail. You may have only a few of those parameters that matter to you. So you really care. You would like to know, p of, I don't know, theta 1, theta 2, and you'd like to get rid of all the rest of the thetas, because these are the two thetas you really care about. Maybe these are the ones you think you're controlling in your experiment. You're trying to determine. And the other ones, somebody already measured the mass of the proton, so you really don't want to determine the mass of the proton again, and you're not going to really say anything about it, even if you did. If your calculation says that it made the mass of the proton a little bit different than what the standard book says, you might believe that in your heart that it's true, but you're probably not going to say it because you're like, oh, I better double check before I do that. But I'm sure that it determines the length of my reactor because I measured that with a meter stick, and nobody else knows that number. So I'm sure that that's the theta that I got, that I'm really going to be in control of here. So oftentimes you do this. You want theta 1, theta 2, but you actually know theta 1, theta 2, theta 3, quite a few of them from that formula. And so you can do what's called the marginal integral. Suppose I have, I don't know, theta 3, theta 4. I can do d theta 3, d theta 4. And this is like integrating out these degrees of freedom to get the probability density that I want. All right? So if you have some case where all you care about is the variance of something, and you don't care about all the rest, you can kind of integrate them out. That's a very handy trick to do. And it's, well, you can do similar things with the Boltzmann things. Like, for example, a lot of Boltzmann distributions, we don't actually care about the momenta. Because what we measure, say, is like a crystallography thing. We see positions of atoms. We don't see velocities anyway. So a lot of times people will just integrate all the velocities out of the problem right at the beginning. So it depends what you want, right? You're in charge of your problem. Any more questions? Yes, Kristen.
Okay, well, I just have an announcement.
Okay.
The class goes today at office hours to talk about KMC, how we grew up from 5 to 5:30, but come any other time to general questions. And we just posted a poll for the final review session. It's either Wednesday evening or Friday morning. So if you could vote on that as soon as possible, that would be great.
Okay, got that. So final review is either Wednesday evening or Friday morning. You have to vote. And if you come today, 5 to 5:30, will be all about kinetic Monte Carlo. And other times today are about anything you want to talk about. And the homework solution will be posted shortly, I think, for the last homework that was graded. Anything else? All right. Good luck as you study, and good luck in the exam.